I am going to show you how to find the solution to all of these electric field, electric force problems dealing with point charges. Okay, so let's just look at some examples. I have some random textbooks here. Let's see if this shows up. So here's a textbook. Here's a problem. If two electrons are each blah, blah, blah from a proton, find the magnitude and direction of the net electric force they will produce on the proton. So here's two charges, the two electrons in a proton. Here's another one. Three charges are at the corners of an isosceles triangle, blah, blah, blah. We're going to do that problem too. We're going to do all these together. Let's look at another another one. I'm not sure which one I will actually solve. I'm going to put that one up. I don't really want that one. Here's another book. 3 point charges are fixed in a right. These are kind of contrived problems too, right? So, and really, once you understand the physics of them, they're all the same anyway. But 3 point charges in a right triangle, blah, 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 negative 6 microcoulombs. What is the force on the charge? Let's see. Here's another one down here. Here's some weird 4 charges on an equilateral triangle with 1 in the middle. Why? I don't know. Here's another one over here. Here's 2 charges at the corners of a cube. Maybe we'll do that one. I don't know. Here's another one. 2 equal charges. They're all kind of weird. Let's look at one more. I got a whole bunch of these books. Here's one. If this is your book, that's fine. Here's one with 2 negatives and 2 positives. And what do they want to do? It's a quadrupole. That's actually kind of cool. How does the magnitude of the electric field depend on the distance? Okay, that one actually I like. I like that one. We can do that one too, though. So let's look at one more book. This is my physics textbook when I was an undergraduate. So again, we have the same kind of thing. Here's 3 charges. What's the electric field right there? Blah, blah, blah. Okay, so let's solve all of these problems. We're going to solve them all using Python, and I'll give you the code. It's going to be awesome. Okay, so the first thing we need to do is understand something about the electric field. So imagine that I have XY axis and Z, but I'm not going to draw that because I don't like to do that. And a charge, I'll call it Q1 right here. And I'll call this at a vector location R. I'll just call it R1. It should be RQ1, but it's R1. And then I want to find the electric field right here. I'll call that, well, I'm going to kind of hard to draw, RO for observation location. I can find the electric field at that location by finding this vector R, where R is RO minus R1, right? Because if I want to find the electric field from the point charge to the observation location, I need to find that. But if I know these two vectors, this vector minus that vector is that vector. Then I can write the following for the electric field. E, I'll call it E1 because it'll be pointing, if it's a positive charge, this would be E1. E1 vector, it's going to be K times Q1. That's not an I, that's a 1. Q1 R hat over the magnitude of R squared. Now, a lot of times textbooks won't write the electric field like this. They'll say, oh, E equals K Q over R squared, which is true. That does give you the magnitude of the electric field, but a lot of times we need the vector value of the electric field. Okay, and so this is how we do it. So again, R hat is a unit vector defined as R over the magnitude of R. And that gives me the direction. So without that, I need to take the magnitude to square the vector. And then all that stuff is a scalar. So I need to make it a vector again. So I need that R hat. Why do we care? Because if I have another charge over here, let's put it down here, Q2. Then this could create an electric field this way, E2. And if I want to find the total electric field, E, it would be E1 plus E2. So I'd have to find both of those electric fields as vectors, right? I can't just find the magnitude and add the magnitudes together. That doesn't work. So I need to do that. So what we're going to do is to build a function in Python that calculates the electric field. So it's going to be a box, right? We'll call it the E function. I won't put an arrow over it. And we need to feed it RQ, the location of the charge. We need to feed it the observation location, and we need to feed it the actual charge, and then it will give us the electric field vector. And then if we do that, once we have a function, we can use that function to find the electric field due to multiple parts and add them up. And the thing is that, remember, how do you add vectors? If I have E1 as a components, E1x, E1y, E1z, and I have E2 as a vector, and I have it in components, equals E2, that's 2, 2x, E2y, E2z. Then the total electric field, E, is just going to be E1x plus E1y, E2x, E1y plus E2y, E1z plus E2z. So that's why we want it in component form. Okay, let's jump over to Python and let's make this function, and we'll test it. And then we'll solve a problem. And there is some work we need to do in a problem, so I'll come back to the paper in just a second. But let's switch over here to Python. Okay, so here we are. I'm using GlowScript VPython. I'm going to give you the code. Don't worry about that. You will get the code. Okay. So the first thing I need is that constant k, the Coulomb constant. I'm going to make this as a global variable, even though some people may not think that's the best idea. I'm going to do that. K equals 9 times 10 to the 9th. And we could put the units here if you really want to, but don't have to. It's Newton times meters squared per Coulomb squared. And I put that as a comment. Okay, so now let's just go ahead and define a function. So functions in Python, let's just make a simple function. I'm going to call it, say, def e. I need to say what parameters I give it. Let's say I give it x and y. I'm just using the name here. And then I'm going to say z equals x plus y, return z. So this is just a brief review of how functions work. So now I have that function. I can actually call that. I can say print e of 1, 2. So what this is going to do is say I'm going to give the function 1 for x and 2 for z, for y. Then the function over here, is this big enough? The function over here is going to say, okay, fine. So I'm going to take 1 plus 2 and I'm going to return that value z. So this should print the number 3. And it didn't. Let's change this. I don't know why it does this, but there. Okay, that worked. Okay. So we don't want to have a function that adds things together. That's kind of lame, but it's an example. Okay, we want our function to give it 3 things. The location of the charge, I'll call it RQ. The location of the observation location, I'll call it RO. And then Q. I'm going to call it QQ because I might read. And you could use a variable that just works in this function, but I want to make sure I don't reuse that variable later on. So now what I want to do is to find the vector r from RQ to RO. I already said what that would be. It's r equals RO minus RQ. So that's my vector r. Now I can go ahead and find the electric field. I'm going to call it E temp. It's going to be K times QQ, right, the charge that I give it, times the unit vector r hat. In Python, in VPython, there is a function to give the unit vector for a vector. It's just called norm r. And then I need to divide by the magnitude of r, and yes, there's a function for that. So I'm going to say mag r, and need to square that, square in Python star star. So I've calculated my electric field. I just need to return the actual value. So I can say return E temp. Okay, so let's test this. Let's say I have a charge at R1Q1 is it's at the origin. I'm going to put it at the origin, so vector 0, 0, 0. I want to find the electric field at 0.01 meter on the x-axis. So RO. See, I don't like that. Let's put this RTO, and then this will be RTO. I shouldn't use R either, but that's fine. Okay, so RO, the observation location, is going to be vector 0.0100. Yes, the vector class is built into VPython, and that's useful. And then let's say it has a charge of Q equals 6 nanocoulombs, 6e negative 9. So now I'm just going to print E, the function. I need to give it the location of the charge, RQ1, the location of the observation location, RO, and the charge Q. And then I could say, we could even do something like this. E equals, and then we could give it units too. Newtons per coulomb. Run it. Okay, and there's my thing. We could check that. I'm almost positive it's correct. Let's do E field calculator example. Save this. Oh, you can't even see that. I'm saving this though. See, I'm going to give you the code. Don't worry. Okay, so here we are. Now let's do. There's one other thing that sometimes we need. There's a couple other things that we might need. Let's put this somewhere else. Let's put this at 0.02 and run it. So it has x and y component. Sometimes you just want the magnitude of that answer, so we could print, do this, print magnitude of E equals mag, and then it's just going to be that same thing. Everything's going to be the same, actually. Yep. Let's run that. And so that gives me the magnitude. And then finally, it could ask for the angle. This one's a little tricky, but let's say theta is going to be the arctangent of, oh, I should do this. Let's do this. Let's call it E1, just so I don't have to. E1 equals that. Arctangent of the y component divided by the x component. So it's E1.y divided by E1.x. And that will give me the angle in radians. I want it in degrees because we usually use degrees. So I can say multiply that by 180 divided by pi. And let's print that. Theta equals theta degrees. Okay, and now you got to be careful with that because sometimes if it's in the third quadrant, both the values would be negative and it'd give you the wrong thing. So you'd actually have to kind of do a little geometry there. Oh, one more thing. What if I put an sometimes they're like, well, what's the force on the particle there? What if I put an electron there? So let's say QP for the, oh, that's GP. QP equals 1.6 E negative 19. That's the charge of an electron. So then I can say print F equals QP times, QP times E1 newtons. So I can find the force if I have the electric field. Okay, so that's that. Okay, let's do a physics problem from the book. So let's get the book. I'm going to switch over here to the camera. I'm going to pick I was working on this problem anyway, so I want to do this one. It's kind of, and like I said, it's kind of weird. Let's do this one right here. Okay, so this says two tiny objects with equal charges of 7 microcoulombs, okay, and are placed at the corners of a square with sides 0.3 meters. So the first one says find the electric field at point B up here. Okay, so let's draw that out. I don't have a place to put my book. Okay, I put it over there. So you can't just plop this into Python because I need to, there's no coordinate system there, right? So I have this as my situation. And Q equals 7 microcoulombs, and the length is 0.3. And I want to find the electric field right there. So the very first thing I need to do is to pick a coordinate system. You don't have to be, it doesn't matter where it is, but you do need to use it, right? So I'm just going to pick this. This is my X, and that's my y-axis. So if that's the case, I need to find the vector location of these charges and the vector location of RO. So let's do R1. The vector location of that is just going to be 0, 0, 0, right? Because I put that at the origin. And then R2 is going to be, this vector is going to be in the x direction, so it's going to be 0.300. Right? That's the location of that charge. Now what about this charge? Well, I'm going to go over 0.3 over 2 and then up 0.3. So RO is going to be equal to 0.3 over 2, 0.30. And these are all in meters. So now that I have that, I can find E1, I can find E2, and I can find the total. Okay, so let's do that. So switching back to our code. So I'm going to here, edit. So I already have my function. Let's just go, I already have RQ1, fortunately, at 0, 0, 0. Let's change this observation location to 0.3 over 2, 0.30. And then Q is going to be equal to 7 microcoulombs, so it's e to the negative 6. E1, there, that's already done. Okay. Then I need RQ2 is going to be equal to the vector 0.300, and then I could call that Q2, but it's the same charge, so I'm just going to leave it. So now I can say E1 is fine. E2 is going to be E RQ2 ROQ. Now let's say the total electric field, E, is going to be equal to E1 plus E2. And I'm going to print that. And I already have that right here. I have the magnitude right there. That's fine. Theta is fine. Oh, that's, I want to print E. Theta. And then let's get rid of that part. Okay, so that's that. So the key here is I had to find those locations of my charges with the values of the charge, and then I can calculate the electric field, run it, and I get nothing. RQ1, RO, QE1, RQ2, E2, E, print E. Oh, let's put, oh, I see what I did wrong. I called that a function. E, let's call that E total. I used the name twice. My mistake. ET is the total. And then let's put this as mag of ET. And then ETX, ETY. Still didn't work. Too many right parentheses in line 18. That's fine. We can make mistakes. Line 18. E, that, oh, I do have an extra one right there. Okay, there we go. So I have 1 times 10 to the 6th is the electric field in the y direction. That seems legitimate. 10 to the negative 6th. I think it's okay. And then the magnitude's 10 a million. And then theta is 90 degrees. Okay, so I'm pretty happy with that. Okay, let's look at the next part. Let's just do all of them. So the next part says, let's see, wait, 7 microcoulombs. Did I do that? Okay. Find the electric field point B, find the electric field at point C, and then we're going to find the electric field at point A. And then this is a good one too. Where would you place a third object? We're going to do all of these so that the electric field is 0 at the corner of the square A. Okay, that's cool. Wait, where would you place a third small object with the same charge? Okay, so A, C, and then where would you put the other one? That's fun. Okay, so over here, looking at our diagram, this is A, and this is C. So ROA is going to be the vector 0.300. ROC is going to be, now I'm going to go halfway over, halfway up. So it's going to be 0.3 over 2, 0.3 over 2, 0. Those are kind of like not even worth doing, to tell you the truth, because it's so easy. So if I want to do this, All I have to do in my code, let's go back to the computer, is to edit this. I want to do A. Oh, I'm clicking in the wrong spot. So let's do part A, point A. All I have to do is change my observation location right here to 0. That's it, right? That's it. I've run it, it's done. That's it. And if I want to do point C, I just change it like this, 0.3 divided by 2. I'm just moving the observation location. And I run this. And that's it. Boring. Okay, now, but here is the question. So let me read it again. Where would you place a third small object with the same charge so that the electric field is 0 at the corner of the square labeled A? Okay, let's go back to the paper. So I'm going to get a new piece of paper because this is actually at least fun. So here's what I have. I have a charge, and there's my observation location, RO. Let's put that as O. So I know that this is going to make an electric field going that way. This is going to be going that way. And so I need to find this electric field going that way, which I know. And then I want to put, actually it'd be more like this. Is that really what it says? Where would you place a third small object with the same charge so the electric field at the corner of the electric field is 0? Okay, that's interesting. So what I can do with my function is actually just change the variable until I get what I want. So I'm trying to think. I definitely want to put it up here somewhere. So let's just pick some x value, 0.3 over 2, and then the y value, I'm going to put it right here, and I'm going to move it up and plot the value of the electric field as I move it up and see what happens. Okay, so I can do that. That's not too hard. So let's jump back over to the code and see what would happen. Yeah, because it is kind of a hard problem. Interesting. Okay, so I'm going to edit this. We're going to make a graph. So let's put down here. Oops, I didn't switch over. I'm sorry. Okay, G1. Oops, again. G1 equals graph. X title equals. We're going to be moving in the y direction. So y title equals E net, the total electric field. And then I need a function F1 equals G curve. Color equals color.blue. Now I need my starting observation location. So I said I want to start it at negative over here, negative 0.3, and then the y value of 0.3. So I'm going to start right next to A. And now I need to pick a step size. How much am I going to move? So let's move dy equals 0.05. I don't know. Let's just do that. Now I'm going to say while RO dot y is how far do I want to move up before I stop. Let's go until RO is less than 0.6, so twice as far as the other one. Then I'm going to do the following. I'm going to first calculate the net electric field, which I've done right here. So E1, E2, E3. No, I don't want to move. I'm sorry. I don't want to move RO. I want RO to be at point A, so it's 0. I'm going to call this RQ3. It's the location of that third charge. It's going to be vector 0, negative 0.3 over 2, 0.30. And then I'm going to move that one. So this is while RQ3.y, the y component while, as long as that's less than 6, then I'm going to do all this stuff. So the first thing I'm going to do is to calculate this Q. I can move up here. Calculate E1. I can put R2 up there. calculate E2, and then calculate E3, which is going to change. E3 equals E RQ3 ROQ. They're all the same charge. And then calculate the total. And then I'm going to plot the y component of that total. So I'm going to say f1.plot et.y. No, I'm going to plot the magnitude of that as a function of y. So y, no, rq3.y mag et. And now what I'm going to do is move the point up, move my charge up. So I'm going to say rq3 equals rq3 plus the vector 0 dy 0. So I'm going to move it up by an amount dy. And then I don't need this stuff, but let's just leave it there. I think that will work. It should make a graph. Okay. And there's my graph. And nothing changed. Why didn't it change? So 9, the magnitude of the electric field did not change. R3Q, I did move it. Let's print RQ3 just to see if that indeed changed. I may have got myself into a little pickle here. Sometimes that happens. It didn't even move it. There's no RQ. It didn't print it. That's weird. So here's the value from 0.3. It did change it because it's over here. Print RQ3. It didn't print it. Did it print it? Oh, it did. It's right there. Okay. That worked. It didn't change, though. Why didn't the total electric field not change as I moved up? Oh, that's why. Ha ha. Plus E3. I didn't add it in there. Okay, that's good. So you can see here that it's going to decrease. My step size is actually probably too large, but over here it's getting closer to 0, but I need to move further away. So let's just move. Let's change this to 0.01 so it has more steps, and then let's change this to. I want it to be close. Let's do closer. So let's do 5. Okay. So you see here it got to a minimum. That's important. Let's actually use that. So 0.55 for my y value. Now I'm going to go up here and say 0.55 for my y value. And I'm going to move the x value from 0. And now this is actually x. I want to start at 0. And I'm going to move it dx, same amount, 0.01. I'm going to move that way. I'm going to move away from it. So over here, I'm going to move this 0, negative dx. Let's just see. And it's going to go from x to, while x is greater than negative 0.6. I don't know. I'm just trying that out. And that did not. Oh, I didn't change the plot. So I need to plot this versus x. Okay, so again, down here you see I get a minimum at x equals very close to the value, which is kind of strange. I think I'm going in a weird direction here, and I think that's a really weird problem, and I'm going to stop. But I just want to show you that you can indeed do these, find the locations by varying the value of the observation location or the charge and calculate an electric field. Let me think about that problem. But I'm still happy with this function. I'm going to give you the code. You can play with it. You can solve a bunch of problems. If you need to solve a problem that's asked for the force at the end, just multiply it by the charge, and you're done. And I'll end there.